morning, all. You are welcome to Thermofluid and Energy TV. So today we'll be discussing how to use Featool to create a cooling chamber. This set of system, you create a cooling chamber. Through the cooling chamber, you can be able to predict the amount of heat that spread through the cooling chamber, whether it's increasing, decreasing, how long the heat is going to, the coolness, how long it's going to take for the chamber to be cooled. So we will be doing this in series, but we are starting off today so that you understand the direct framework on how to use Featool as an engineer. Featool is a very good simulation tool for you to predict heat transfer within a system. You understand the amount of heat that is transferred through a body like a refrigerator and others. So you'll be able to predict, okay, this is the amount of time it's going to take for us to cool this material or these substances using your cooling systems. So now you can see, just watch my cursor. We are starting afresh. Let's assume you go to file and you just go to file, look at my cursor, you create a new model. This new model, as you can see displaying here, you have 1D, 2D, asymmetry, and 3D. So you just come to 3D, you click 3D, and you are okay to go. The dimension is in XYZ dimension, and the physics we are using behind this is the heat transfer physics. You can see it behind here. So you come up, you press OK. So after doing that, you have set up the system. You can see it by my left on the screen. So the next thing you have to do is to take the geometry of the system. So what we are using, you come to geometry. What we are using here is to create an object, and we are using, by the geometry side there, you can see create an object, and we are using block. So you click that block, then you see create the block. For each side, like I told you, you have the minimum and the maximum side. Look at my cursor on the screen. So you have the X minimum, X maximum. The minimum is ordinarily starting from root, which is 0. Then the maximum, which we take a length. For what I'm cooking, you can put any length there, whatever length you feel you want to use. Whether 10 meters, 3 meters, 4 meters, 7 meters, depending on how much length you want the heat to transfer through. So now I'm starting from the root X minimum, then the maximum length I'm using is 0.56 meters. Then Y minimum and Y maximum. So we take that as our width, which is 0. Here you click Y maximum. Y minimum is 0. Y maximum, we are taking 0.3. Then Z minimum is 0. Z maximum, we take another configuration. Then we take 0.4. Then we OK. As we OK it, you see the box. So the property we want to cool inside this box is going to be tomatoes. Let's assume we build a system that can preserve tomatoes for a length of time. So we assume this whole block you are seeing here, we assume is all filled up with tomatoes. So since we assume it, now we have to come and fill in the details, which is the equation. So you come, look at the dialog box, you see equation at the top there. So you go to equation, the equation mode. So you are to set Your own is to set. So that you reset, you come to equation setting. So you go down, and for what is what, we are going to use the equation editor to edit what we want. So from here now, you see the heat transfer. Heat transfer. You see the equation at the top here. Look at it on the screen. Then on the first equation coefficient is the density. You see the density there. Watch my cursor. Then as the density, for tomatoes, we assume is made up of over 90% of water. So we are using the density of water. So you put 1000 there. Then the specific heat capacity for water is what we are equally using. We just put 3500. Then the thermal conductivity, we put it there too. Thermal conductivity, we put 0.5, which is the thermal conductivity for water. Then the initial temperature. The initial temperature, what we do there, because we are putting an initial the temperature that before it enters inside, what should be the temperature. So what I'm building, for example, I'm assuming there is a PCM between the tomatoes and source of energy. So we assume that the PCM that is going to cool these tomatoes is going to be like the outer temperature, that is the initial temperature from outside, is going to be like, you assume how many, what should be the temperature for tomatoes within Nigeria region, for example. So okay, this temperature is going to be around 35. Nigeria temperature is around 35 degrees Celsius. So you put 308. We are using Kelvin. That is what Featool use. Featool use Kelvin as is a temperature unit. So after filling that, you you go through your you go through your temperature, you go through everything is okay. So you what you do add is to add is to apply. You just apply. You come under it to look at my cursor there. You just apply, then you press OK. So you solved the temperature. Then you now come to the boundary conditions. You come look at the top of the listing again. You see boundary conditions there. You see the boundary condition. So you just again you come to boundary setting. You come to boundary setting. So you can see the boundary there. So for one, you can see the top under is going to be a convective flow. So you are not changing anything here. You just apply it. You just apply. Then you come to from 2 to, you just come, you highlight from 2 to 4. From 2 to 4 is going to be convective flow. It's going to be convective flow. You apply and you say OK. Then you come to solving. But before you solve, you can come to the grid. You come to the grid. Which grid do you really need? That is, the grid is how fine, how thin is your boundaries. How thin is the boundary? How thin is the tomatoes? Are they smooth that they are like water? The heat can just transfer through. You can see the mesh. Is it mesh on what we are building now? Is it smooth? Is it just going to go in smoothly like water, or it has some coarse region that it should go through? And you know, tomatoes, what we are cooling is tomatoes, so it's not just going to be smooth and it just going there. There's going to be some coarse because they are thick, and for that you have to refine. You have to refine it. You refine. You try to refine again, and you can leave the mesh like this. because we are trying to transfer this heat through tomatoes. You leave the mesh this way, then you come to solving, then you go to solver setting. At the top of your screen you see the dialog box for solve, then you come to solving this. So what we are solving is it going to be stationary or time dependent? You can see the top of the solver. Is it going to be stationary or time dependent? So since it's not just one place, we see the heat is changing per unit time. At a specific time, this is the amount of heat that goes in. At a specific time, this is the amount of it. So we put it at time dependent. So if it's time dependent, we need to get our time step. Is it going to be per how many seconds? Is it going to be 10 seconds? Every 10 seconds, this is the change. You can see the time step under that time dependent setting. So is it going to be 10 per se? Is it going to be every 5 seconds, every 10 seconds? So for us, we believe you can put any seconds there that you want to monitor. But for us here, we just say 60 seconds, every 60 seconds. Then for how long is it going to be simulated? You come that is simulation time. So let's assume we want to simulate and know for 2 hours. So you multiply 60 times 60. You multiply 60 times 60 times 60. Then that is 60 seconds times 60 minutes. That is 1 hour. Then for 2 hours, it's going to be 7,200 seconds. The 7,200 seconds. So then you have your criteria. These are already applied. You leave them there. Then you check if there's computer solution. If there's anything you need to compute, the time is okay. So you come to your okay it. You come under you okay. Then you go back to solving. Come to solver setting. Since you have an already prepared manual, you can solve. You solve. Just solve. Then you watch as it initiates the solving. You see the linear solving, and it's already solved. So this one solved within 2 hours. Then you look at the amount of heat that flows in. It's within that region. You look at the chart, the color chart. You see that within that time, the amount of heat that flows in fell within 307 degrees Celsius, Kelvin to 308. So the material was only cooled insignificantly by just 1 Kelvin. That is what happened. So for today, you've understood how to use this system to calculate heat transfer. And next week or next time when we meet again, I'm going to teach you how to use it to calculate real time. As you are doing it real time, you understand the heat and how you can take your readings, take your calculations, and know the amount of time that it flows in and what happens. So this is our first edition in this series. In the coming edition, we'll be taking how to use Featool to another greater height. This is just a beginner stage, and you understand what is being done. So we thank you for watching. You can love our page, subscribe, and with all this, we'll grow together as engineers. I'm an expert in this field with my PhD, and I believe you too can learn and become an expert in this field too. Together we'll grow and we'll be able to build things that will take our names far and prestigious within this field. Thank you. Bye-bye.